okay? And one of the ways we treat those is to give them a bunch of oxygen because it can be lethal to them, okay? So, there's two ways to think about this. At the cellular level, why do we need oxygen? Okay, so what happens in the cell with the oxygen, that's one way to talk about respiration. They call it cellular respiration then. The second one is, what's the system that allows us to get the oxygen down to the tissues? And this is going to overlay really well with the circulatory system because that's ultimately what we're going to give the oxygen to take it down there and then move it across the capillaries. But we're different than a lot of organisms, okay? We're the pinnacle of evolution, right? We're mammals, okay? Humans, okay? So we must have the most specialized system for oxygen to get into our body, and that's a bunch of crap. We suck at this, really, okay? We just happen to move out into an area out of the water where now there's a lot more oxygen out here, right? And we can take advantage of it, okay? Actually, fish are better at doing this than we are, okay? They can extract more oxygen from their environment than we can. They have to be able to because there's so little oxygen in the water and there's so much out here, okay? So we're going to be out doing this kind of stuff down here. We're going to talk about an organism. We'll be talking about humans, okay? How do we breathe? What's the mechanism that's there? We understand gas exchange because we know that these gases are lipid soluble. They can pass right through. So all we gotta do is get them down to where it's really thin enough for us to move them across, and we'll do that, okay? And then we gotta regulate it, because I don't know about y'all, when I get on a treadmill, I breathe harder, right? Because I'm using more oxygen, and I'm producing more. Why would I produce more carbon dioxide? Where's this carbon dioxide coming from, y'all? But where did they get it? Where does the carbon, that C, where does it come from? No. Cell makes it.
No, use
Plants.
Not from plants. Well, you can say that maybe. Ultimately, the ultimate source would have to be plant, but it's what we eat, y'all. It's the carbons in the fats, sugars, and proteins that we eat. That's where all that carbon comes from, okay? All three of those things are carbons, hydrogens, and oxygens, right? So, every bit of the carbon that we take in as, if we don't use it to build something, we take it in as food. If we don't use it to build something in the body, it's going to leave us carbon dioxide. Okay? So, that's where this regulation is going to come into play. So,
if I may ask, at the beginning of this lecture, you asked of respiration, you asked a question about the oxygen and something, and you said, somebody said use it for ATP, right?
ATP reduction.
So then you go back to the first slide. So is that in respect to cellular respiration, what use of oxygen and carbon dioxide?
Yeah.
Is that the point you're trying to make?
100%. Okay, so on our planet, we have different amounts of oxygen in different environments, right? Okay? In the water here, we can't breathe water, right? Why can't we breathe water? We don't have the ability to extract oxygen from water very well.
We don't have gills.
We don't have gills, okay? We don't have the ability to do it very well, okay? Now there's some things that you can actually do this with. You have to take special, put drugs in your lungs and that kind of stuff that causes them to be able to absorb more oxygen and that kind of stuff. It still can't do it for very long. It's kind of cool, yeah. You be a mermaid. Yes. Okay. So, if I reached in my pocket and I pulled out a 1 liter container, vacuum packed, nothing's in it. There's absolutely nothing inside of it, right? There's no air, there's nothing in it, it's empty. What is it? It's empty. Okay? And here's what I do. I unscrew the lid and I go, air comes in because it's vacuum sealed, right? Air comes in, and then I put the lid on. Now I've got a liter of atmospheric gas. Y'all agree? Got a liter of it in there. If we analyze that, it would be 78% nitrogen, 21% oxygen, about 1% of some other crap that's in there, like pollutants and things like that. Maybe some perfume that, or deodorant smell, or whatever it is, right? Maybe some viruses floating around, that kind of stuff. And 0.03% carbon dioxide. And Al Gore would say, and there's more now than there used to be with this carbon dioxide, right? Okay, and that's true. Not just so we know now in the water there's less than that. How much less? Check this out. If I did the same thing and I did it underwater, opened my little vacuum packed thing, closed it back up and filled with water, that'd only be 5 to 10 milliliters, not 210 milliliters of oxygen, but 5 to 10. A lot less oxygen, right? That means that's what the fish have to do. They got to deal with 5 to 10 to get enough oxygen for them. Okay? They got to be better at this than us. It's cool.
Yes.
It's cool. Okay? So, we had to get up the hills. And notice that when we find all these land organisms, they switch to something that's for terrestrial use. Okay? All right. Let me ask you this. Is there more oxygen here on the trail or up here on top of this
On
mountain?
the trail.
Does it matter?
It's a trick question because it's all atmospheric. It's all the same amount of oxygen.
Ah,
That's cool, right? It's still 21%. What's the difference? Pressure. Pressure. Not the amount of oxygen, the pressure. Okay? So, that sets the stage for us having to use pressure now. Pressure is going to be the whole way the system works. Okay? We're going to use pressure. Since there's a pressure on the outside, okay, we're going to be able to use that. So, environmental conditions. What is it if it's anoxic? There's no oxygen. What if it's hypoxic?
Too much.
There's not enough. Normoxic, the normal amount of oxygen, which is 21%. Hyperoxic, too much. Got too much oxygen now, which can be lethal to humans.
Excess.
We don't do well with pure oxygen. Okay? And we'll talk about that. It can be lethal to us. All right. Let's do some math right quick. But then let's not have to do any math, really, right? There's an equation that shows us how diffusion works best. It's called Fick's law, and Fick's law says if I want things to diffuse well, I really need 3 things. Okay, 3 things to make this work well. I need a big surface area for diffusion to take place. That makes sense. Okay, I need the distance that it has to diffuse across to be small. Y'all agree? Okay. And the third one is I need there to be a big difference between where I need there to be a lot on one side and not very much on the other. Because it doesn't do real well if there's like 51% and 49%. We don't get good diffusion then. But if it's 100% and 0, it diffuses really well, really fast. So those 3 things are going to help us. Okay?
I didn't answer give this.
What?
The points you gave me.
So 3 points. Increase the surface area.
So where is this going?
Distance across, difference between area that we do it with.
Yeah,
So
where
this is surface area. This is the differences in the concentration from one side to the other. And this is, how thick is it?
How thick?
How far does it have to diffuse? What does it have to diffuse across? Okay? So, that's the things that we're going to work on. Okay? Now here's some other organisms out there in the world. Little single cell, yeah. What? What about it? That one? Yes. Okay. And then that diffusion constant is just to get your units right? You gotta have one of those.
So you said the Francis concentration. What do you mean by Francis concentration?
If there's a bunch and there's very little, it diffuses faster.
Oh, okay.
Okay?
Then what about the distance across which diffusion takes place?
How big is the area that, or the surface area, the area over it? The bigger the surface area, the more diffusion you can do.
Oh, okay.
Okay, so those are the three things that we're going to work on, okay? Now, if we're a single-celled organism, we don't need a lot of oxygen, do we? Doesn't need a lot of oxygen, so it can just get what makes its way in and what makes it leave, okay? So oxygen comes in because oxygen is going to go from area of high concentration, area of low concentration, right? We call that diffusion. So oxygen is going to diffuse in, and if there's more carbon dioxide in the cell makes more energy inside the cell. Is there going to be more carbon dioxide on the inside than there is on the outside? So carbon dioxide would leave. Cell made it. Okay? So notice, oxygen coming in, we don't need a respiratory system, is what I'm getting at. It's small enough, and the amount that is necessary to run the organism is small. Okay? Let's move to an amphibian, okay? Let's make it a little salamander, And this one doesn't even have any gills or lungs. It's a lungless salamander. We got those. They get everything they need from the skin, okay? Okay, respiration happens through the skin. So we just put the blood supply up close to the skin. Any of y'all worried about getting eaten by a salamander on the way home today?
They're so cute.
Nobody's worried about it? Why? Because they're little bitty, right? They're little bitty. That's not going to eat you. And that's an issue. In order to do this, you got to be small. Okay? Because there's a limit as to the amount of oxygen that's going to make its way in here. What if we're a little bit bigger? Let's be a starfish, y'all. You know the little bumps on the outside of the starfish? Does that increase the surface area?
Mm-hmm.
Yeah. So now they can take in more oxygen because they got all this extra surface area from the little bumps, or papillae they call it, on the outside of the starfish. Even insects, little insects, if you see a grasshopper or something like that, they've got holes on the outside of the body that allow the air to come in and for gas exchange to occur. They got a whole plumbing system inside their body of just open holes. Okay? We're talking more about fish. Then we've got the pinnacle of evolution, y'all, mammals. We've got lungs. We put it on the inside of our body. Notice all this other crap is on the outside. We're putting the lungs deep inside of our body. That makes it a problem for us because we got to get the oxygen that we want in here. I got to get the carbon dioxide out. So I have to have a ventilation system that's going to work. Okay? If I'm a fish, I just let y'all know how sharks breathe?
Gills. They gotta move. They gotta constantly keep
They
moving.
got to keep constantly moving. And here's how they do it. They just open their mouth.
They're so
Water goes in, and out their little gill slits. Constantly. And they're just extracting that oxygen from the water. Okay? It's called ramjet ventilation. I love the name of it. Okay? That's even when the shark is asleep, it has to be swimming. Okay?
Except
Imagine
for the
running
nursery
into-
shark.
Running into something, maybe a new ship sank in the middle of the ocean, and then you just bam right into it while you're sleeping. Okay.
Do they sleep with their eyes open or closed? Or do they sleep with their eyes open or
No, their eyes
closed?
are pretty much open.
Yeah.
So you really can't tell.
Conscious?
They do have this ability to cover it, like you see the sharks that'll do that, yeah.
It's a little film.
Yeah. It's a little film that covers, that way they don't lose their eyes if they're thrashing up against something that, and you got a pokey thing on it. Okay, so look at this. This shows you, and I like the way that this is set up, oxygen's gonna make its way in when we breathe in, right? And we've got set up this system where the blood is right on top of this lung part, right? This alveoli, we'll call it. This alveolar sac, that's what that is. Now look at the way it's set up on it. Notice that I've got the venous blood, which has oxygen or no oxygen?
No.
It's deoxygenated, right? And it's going to turn red, okay, and make its way there. So that red is ultimately going to turn into what before it gets to the heart? The pulmonary. That's good. That's good. So this is really the pulmonary artery sending it right Isn't that crazy the way you really have to think about it? I still do, y'all. Okay, that's the pulmonary artery. And that makes that the pulmonary vein. Okay? Okay, look at how it's set up. And I want to come back to this because they've done it well here for us. Which way is the oxygen coming in? From right to left?
Yes.
Let's say the oxygen is coming in from right to left. Right?
No.
It's gonna do this. Oxygen's
Oh,
going
yes.
this way.
Okay.
Okay? And blood's going this way.
Mm-hmm.
Y'all agree? Okay, that's important.
So where you said blood is going to?
From blue to red.
Oh, okay.
All right. So,
But you said the blue takes blood to the vein, right?
no. Blue is the pulmonary artery. Getting oxygenated in the lungs, remember? Blue ones are arteries and the red ones are veins in the pulmonary circuit.
Oh, okay.
Okay, so here we are in Denton, Texas, and let's say spring break's coming, so we're just gonna leave today. We're gonna go on down to, let's go to Port Aransas,
Wow.
okay? We can watch the whooping cranes, that kind of stuff. Stay a little bit away. We're still close enough to make all the parties, right, on the beach and that kind of stuff, but we're gonna stay in. Anyway, we're there at sea level. Y'all agree? Because right out our hotel room is the sea. Okay? And at sea level, the atmosphere weighs the most. Now, does this air that I just caught, does it weigh something? Yeah? It weighs something, right? Because it's made up of nitrogen atoms and oxygen molecules, and there's probably a little water in here because y'all been breathing out a bunch and that kind of stuff. Some carbon dioxide, and all of those atoms weigh something, right? So if we're at sea level, we have the entire atmosphere on top of us. Okay? How much does that weigh?
You
Well,
said,
there's a pressure exerted from that. Let's make it that. There's a pressure exerted. Somebody called it 1 atmosphere, which I thought was brilliant. Well, it's 1 atmosphere. Let's just use that as our unit. Then some people, 760 millimeters of mercury. Okay? Just like we had millimeters of mercury on the blood pressure, units of pressure. So there is this pressure being exerted on us at sea level. How much? 760 millimeters of mercury. And that is the 78% nitrogen that's above us, the 21% oxygen that's above us, the 0.03%, and the 1% of other crap. All up there. And it changes as the weather happens, where there can be more humidity in the air or less humidity, and we call that barometric pressure, right? That's what they give you on the news. Y'all watch the weather sometimes on the news? And you can actually, they've got these own barometers that say, as it gets lighter, that's going to be clear. As it starts getting, the atmosphere gets heavier, storms are coming in because moisture's increasing. It makes pretty good sense, okay? So, we can actually calculate oxygen's part of this 760, because all I've got to do is take 21% of 760 millimeters of mercury, and that would be the partial pressure that oxygen provides to it. And we could do 78%, and that would be the amount nitrogen, and 0.03 would be the amount that carbon dioxide gives to this, okay? So pressure's going to be a big deal, okay? Pressure's going to be a big deal. Now, what we worry about is oxygen, okay? We worry about the pressure of oxygen. That's what we want to get in the body. And likewise, carbon dioxide. Okay, so here's the deal. We're at sea level. We're, Port Aransas here, okay? And we're gonna take a trip, y'all. We got 1 week of spring break. So we take off, leave Port Aransas here with 760 millimeters of mercury, where if you take 21% of 760, it gives me 160 for oxygen. Partial pressure of oxygen, 160 versus 760 for the whole thing. Everybody good with that?
Mm-hmm.
This is the whole thing down here. That's oxygen up there. Same scale. Here we go. We drive from there. We drive we are 4,350 meters above sea level. Okay? Y'all, it's hard to breathe here. On the way there, we stopped in Denver. They were having pint nights in Denver. We did a little bar crawl in Denver. It was hard to breathe. Why is it hard to breathe?
Because of pressure.
Pressure. Here's the deal. It's all going to be about pressure. The greater the pressure out here is, I have to make a less pressure in here to get air to come in, right? Less of a pressure in here. If there's more, does pressure always go from high concentration, low concentration? No, from high pressure, low pressure. Let me say it again. Does high pressure go in nature from high pressure to low pressure?
Yes.
Can you air up your tire by sticking a knife in your tire? No, because there's more pressure on the inside of your tire is coming out. Agreed? Okay. So this is what we're going to do. We're going to go from high pressure to low pressure. When I get here, is there less pressure out there?
Yeah.
Okay. Here's how air comes in. We don't think about this. Not one of us in here breathes this way, where we grab a volume of air and force it into our lungs, right? We don't go. Every time we breathe. What we do is we increase the volume of our thoracic cage. The whole thoracic cage. That's what I have access to. Remember, muscles move bones, right? So I can do this. And increasing the volume here makes the pressure in here go down. All I got to do is beat the pressure out here, right? All I got to do is be lower than the pressure out here, and oxygen is going to come in. Y'all agree? Does that make sense?
So you lower the volume of pressure in your
Now increase the volume, which lowers the pressure.
Okay.
Okay? We're an accordion, y'all. Take the accordion handle, both accordion handles, and you do this. Which way does air go? In. If I do this,
Goes
out. With in, out, out. Okay? We're doing the same thing. We're decreasing the volume, air comes in. I'm increasing the volume, okay, which causes pressure, I'm decreasing the volume. I'm increasing the volume, pressure comes in. I am increasing the pressure here, volume goes out. Okay? So we're doing the same
When you
thing.
are decreasing the pressure, the volume goes out. With the accordion?
If I decrease the volume, it causes pressure to go up and the air will go out. It's all about pressure.
When you do this to the accordion, what are you doing?
I'm increasing the volume, decreasing the pressure in here.
Okay, so when you decrease the volume, what happens?
I'm increasing the pressure, and it always goes from high pressure to low pressure.
Also, when you decrease it, pressure increases. Is that what you're saying? When you decrease the volume?
When I increase or decrease?
When you decrease the volume?
When I decrease the volume, the pressure in here goes up and air comes out.
Or do you mean the pressure in the accordion?
Yeah.
It will go up. And
There's
go
two
up.
pressures. There's one in the accordion, one outside.
Okay, when you increase the pressure, when you increase the space of
Increase the space.
of the accordion,
Makes the pressure in here go down, which means the pressure out here is greater than it is in here. Air is going to come in.
or air will come in. So when you decrease the space of the accordion, what
Increases the pressure, air goes out. Okay? How do I blow air out? If I've got it here in my mouth,
happens? So
I have to do that, which is decreasing, it's causing pressure on it, which will allow me to blow it out.
okay, if I do this now, the volume has increased, the space. So is the pressure less there?
Well, you make the pressure by here on your mouth. You can make it real hard to hold it. Yes, you can make it really hard to hold in because if you squeeze a lot, right? Go like this.
So when you do that, so the pressure is down.
Pressure's greater in here than it is out there. So the air goes out. Okay?
Okay, now.
Okay. So here's the deal. We're doing the same thing. We get to Denver. It's harder to breathe. We notice it's harder to breathe. Why is it harder to breathe? the pressure outside is less now. We used to just have to beat 760, right? How much do we have to beat now?
We are not 400, right?
So, let's say we're here. We used to have to just get below 760. Now we've got to get our lungs, that thoracic cavity, let's call that 450. What is that going to mean? So here's our normal, let's beat 760. That's easy. How do we beat 450? Right? So what is that going to look like here? A lot bigger breath, just to get the normal amount in I used to. Okay? What did we do in the blood when that happened? What did we do in the blood to make this be easier for us?
Create more blood cells.
How do we do that? What was the hormone that the kidneys released? Erythropoietin,
Erythropoietin, yeah.
right? We release erythropoietin because we are hypoxic in the blood, not enough oxygen in the blood. How long is it going to take? 7 days. So we're gonna be in Denver for a while, y'all. We're gonna find all the good places to drink and eat and that kind of stuff and have fun. And now we're gonna start moving up again. We're going to Mount Everest, y'all. Look at the pressure there. We're talking about maybe 275. How's that ventilation gonna look? Every breath is gonna be the biggest breath that we can inhale. Okay? So what they do is on Mount Everest, and it says here, we don't live very long above 6,000 meters, okay? They make the plan. We're gonna make the ascent today. The weather's good, we're going to the top today. Y'all ready? Let's go. And we start booking it up there. We're going up there and we're coming back. Same day. We ain't staying up there long. We get our picture made, little selfies, everybody get in a group. You good? And then we gotta get back down. Okay? The trail up to the top is littered with bodies, y'all, still. We can't get them off. It's too high. It would be too energetically expensive to do that. So people that have died doing this, they're still there. And with the global warming that's happened, a lot of them are actually starting to see them again because there's been enough melt that people that have been buried for 50 years. Oh, there's old Jack over there, remember? No, I'm just kidding, I don't say that. Isn't that awesome? It's cool.
Just froze.
Hmm?
Just freeze.
Yeah, it's cold as crap
You
up
can
there.
look the same. So they're Captain America.
Hmm?
They're Captain America, yeah. Exactly. But without superpowers.
Yeah, so they're just frozen like somebody put them in the freezer.
So,
They're not decomposing at
They
all.
wouldn't decompose at all.
Well, I
Would
mean,
you
just leave
probably
them
a
there?
little bit maybe, but there's no animals up there to eat them.
They're like so why can't you have like any like machinery like a helicopter or something like that to get them?
Because people are gonna have to go out and chip them all out and all this
Find
kind of
them.
stuff, yeah.
There's not like a
And find
Sherpa
them.
out there that'll go
What?
down and like one of those Sherpas that takes you up there. There's not. They don't.
They ain't gonna, they're the same.
I think
So,
so
I read a book
a
about it
person
one time. It was pretty
over,
cool. It's been a long time since I read the book, but they were just bodies littered along. As you're walking along, there's somebody, there's somebody over there.
It's called Rainbow Valley because of the amount of jackets and
Yeah.
various colors.
I just liked your face. Yeah.
so a person can't adapt over time?
What?
A person cannot adapt over time?
Well, sure. We can adapt to our limit, though.
Your limit.
Right? To our limit.
So, like you're saying, how humans can't live above, or can't live long above 6,000 meters. So how do people get up to the top of Mount Everest? They
Most
don't.
of the time, at base camp, there's oxygen. So we're going to fully oxygenate ourselves. Try to make this up, okay? And come back down within the amount of time that we can do this.
Can you not bring oxygen tanks up there?
There are people that do that, but they consider it cheating.
Yeah, but if I did Mount Everest, I did it.
I'm with you.
I don't care if I cheated.
Yeah, me either.
I just
right?
did something.
Me either. Helicopter just dropped me on the top for a minute. Selfie, I'm done. I was here on top of Mount Everest. You climb Mount Everest, You know, that's what I do. You don't ever answer the question, right? You just keep talking about it. You know, it wasn't that big of a deal.
You don't take my now, there's the top now for us.
Yeah. I'm in the top. I mean, it's not really a climb. It's more of a walk. Walk down
Are
the
we-
helicopter.
As a species, is the human
Crawl
race,
out of the helicopter too, right? I crawled my way up to the top of Mount Everest. See?
but as a human race, are we still evolving as a species?
Ooh, absolutely, 100%. Everything is.
So how do you evolve to the next species?
Well, I can tell y'all, as a species, we are now taller than we've ever been as a species, that we are losing our teeth, where some people are, over time, used to be wisdom teeth were much more prevalent. Now, not so much because we're eating more meat. Meat eaters don't require the same number of grinding molars and that kind of stuff, right? And you could make it so much as we have immune system cells now for things that we never had immune system cells because those just came around, right? So there's lots of ways that you can do this. I remember we went to Valley Forge where Washington was, and they had the cabin there that they were stayed in. And y'all, I stood in the door, my head touched the top, both my shoulders touched both sides. I was the door. I mean, seriously, I'm like, they were little bitty. Okay? My wife lived in England in a 500-year-old house. Her dad was 6'4". When he came down, he hit his head every morning on the stair above because they weren't that tall back then, right? So, yeah, we can say that there's definitely some changes going on, and it better be continuing to happen, right?
Better be.
Because all evolving is changing the frequency of genes over time. Okay?
So, just wishful thinking,
Yeah.
like the movie Waterworld.
Yeah.
You think that's ever possible?
I mean, we're talking for something like that
Like a
would
millennia?
probably be more of a mutation if a mutation like that happened that allowed that person. Now, there were several things that went wrong. We had webs between them, gills, all that kind of stuff. So put all that together, it'd take a while. Like hundreds of thousands of years.
How about our intelligence?
Well, I figure we're probably those. Would you assume, well, first of all, is intelligence something you look for in a mate?
I would think so.
Is it?
I would. See, but the thing is, okay. If there's, I'm sorry, I'm bringing us down a rabbit hole, right? I'm sorry,
This is
but
good.
like Neil deGrasse Tyson, a physicist, right? He once said that if there's a being that has 1% difference in intelligence than us, right? Would we be able to understand that being as a species? Right? Because there's a 1% difference between us and chimpanzees, but we treat chimpanzees the way we do, put them in cages and have them do tricks for us.
Another thing that goes with that species concept is can you reproduce with them and do you make viable offspring? Right? It depends on the definition of a species that you're dealing with. What he's giving you is how far genetically apart are things, which is different from like a donkey and a horse. They can make a mule, but mule is sterile.
Right.
They can interbreed, but it's not viable. That's why they're two different species. Okay? But then you have things like ligers, where you put a lion and a tiger together, and we can get them to do this, but it should not happen in nature. That should never happen in nature.
Mm-hmm.
Right?
Yeah, but we're also having polar bears with brown bears mating, and you got, and it's happening. Could that happen with us? I mean,
I don't know of something else out there that we are genetically viable to produce offspring with. You know what I'm saying?
Right.
I mean, one of the questions back in the day is, did Cro-Magnon man, were there two species back then? Did one beat out the other?
Mm-hmm.
Right?
Yeah.
Or can we still find some genetic variability that due to inbreeding and that kind of stuff? Don't know. But we see it a lot in animals, but a lot like wolves. Okay? If y'all go find a wolf on the mainland, any wolf, it's got coyote DNA in it now.
Yes.
What?
Coyote.
DNA. Every wolf in the mainland parts of North America has coyote DNA. There's only one group that lives on an island out in Lake Michigan where they got stuck there. They can't swim far enough. They're just stuck there. They're the original wolves. Okay? Now, are they worth protecting?
Yeah.
Yes.
I mean,
And that's what, I mean, it depends, and I appreciate that. Some people, yeah, because they're, how much y'all willing to give of your tax money to do this though? Would you rather spend it on COVID vaccines, or y'all wanna, and that's where a lot of this
But,
See, but what gives us the right?
environment stuff, and this goes into Republicans and Democrats.
Of course.
It goes all over the place with this kind of stuff.
Just because that's what I'm talking about, our intelligence. Just because we see ourselves as a higher being, right? What gives us dominion over that wolf population saying, because my importance, because my intelligence is higher than yours, I have rule of how you live,
But we
and
do.
that I
But
know.
we do as humans, and that's, guys, this is exactly what we're doing with health right now. Healthcare is the same way. Why does insulin cost as much as it does? Why were they allowed to make the EpiPen that saved people's lives cost $500? Yes. Dude bought the company, it went from being $50 to $500 a pen. Okay, why? To make money, right?
That's capitalism.
And it's sometimes wrong.
That's why people go on the dark internet, black market, and they buy the stuff
Right.
illegally.
And that's why we have rules that say we shouldn't do that kind of stuff too, right? I mean, it's,
Of course.
we're our own worst nightmare as humans, right? We've made up the rules for every other organism on this planet to live by.
Yes.
When you get to thinking about it, there comes a point where we're in charge of that little snail in some creek somewhere. We can't build a housing addition because that's an endangered snail.
Yes, and that's a big,
And people will be like, a snail.
yeah.
But I can make $1 bazillion.
Mm-hmm.
You know?
Like here in Texas now, the newest thing is not the newest thing is the zebra mussels.
Oh, yeah.
You know, like,
I know.
all right, I get. I'll bring us down a rabbit hole. Sorry.
It's, I love where you're going with it. Think about it from the healthcare side. Most of y'all are going into healthcare, some form of healthcare.
Right.
Okay? And that's where we're at with accessibility, how much stuff costs now.
And affordability.
Right, because when COVID broke out and then Pfizer came out with the vaccine, you know, the biggest argument was make the technology available to the world, and they didn't want to do that.
Right. That's exactly right. They patented it.
Of course.
And that's the way capitalism works. They got to make their money too. You know, if you got trapped over in Europe, you had to be tested before you could get on a plane.
Mm-hmm.
Okay, so they were free here for us, right? I got 6 boxes sent to me free to test. You know how much it costs people to fly home? $500 to get tested.
Because when a new drug comes out, it takes literally 15 years for that drug to hit the market.
Sometimes, depends. But, yeah, you're right. A lot of testing goes on, a lot of stuff.
Okay. Sorry, guys.
And we as voters have the ability to change things.
Yeah.
And that's the way our nation is set up. The only way to change it is to put people in or take people out that we don't agree with what they're doing.
So back to my original question is, as a species, will our intelligence increase? Do you think that? Because I think that has to do with intelligence.
So, first of all, we'd have to say, is intelligence something that you inherit?
Not necessarily.
Okay, so if it were something that you inherited, then if people selected for, it's like, suddenly really smart people are, in our heads, very good looking people, right? This is somebody that I want as a mate. This has characteristics. We all choose a mate, right? Based on what we desire in that mate, right?
Mm-hmm.
There's gotta be something. There's some reason. It may be that they're good looking. Maybe they got a lot of money, right? They drive a good car. They have a great heart, right? They rescued me. She rescued me when I was drowning. And we, there's something that made them attractive to us.
Mm-hmm.
That's one of the things that we think about with producing offspring. I want that. And it's kind of subconscious, but I'm looking for traits in somebody that I would want in my offspring. That's what a lot of other organisms do. Why does the big buck get to mate with all the does?
He's the strongest.
Got the strongest. He's got antlers.
Because
biggest
the doe,
antlers.
it's the doe's decision who they mate with. It's the female's choice, y'all. In nature, it's the female's choice. She's the picker.
Yes.
What does the buck have to do to get picked?
Fight all the other
Fight
ones.
off everybody else and be present when the time is right.
Yep.
Okay? And she does the picking. So in nature, we got to be the red cardinal, not the drab cardinal. We got to look good. Okay? With certain bird species, the males get up and dance for the females, and they pick. That one did it right. I'll take that one. If you fall, go on, right?
Mm-hmm.
So it's how you're selected. So it would have to be selection for intelligence.
Selection.
And even then, is it genetically? Is that something that is genetically passed on?
Okay, but we're getting to the point where we can genetically modify that stuff, like CRISPR
Sure,
and Cas9 and all that other stuff.
I do. Yeah, but can we do that?
Not yet, but we're getting there.
But can we do that? Is that something they allow us to do?
Here
That's
in the
the whole
United
thing.
States, no.
But that's the thing, right?
China's
We're
already-
we're self-governed,
Mm-hmm.
right? Supposedly, we're self-governed.
All right.
Good talk. Y'all have a